Okay, guys, welcome back. This is Chris Key from Life and Home Chemistry Shorts. Today we're going to be talking about oxidation numbers, and this is kind of a lead in to redox reactions, oxidation reduction reactions. So this is kind of the building block, the foundation that you need before we jump into those types of reactions. And oxidation numbers, I know sometimes can be confusing. I've heard students in the past, it can be confusing because is it the same as charge? Is it the same as the normal charge of an atom? And there is some overlap, so that can cause some confusion. But what you have to think about this as is it's an accounting system for the electrons. Now, with any accounting system, like if you're working for accounting for a company like a bank, your main job is to figure out the flow of money. Where is the money coming from? Where is it going? And that helps you keep track of it, so you know where it's at and where it's going. This is a similar thing, except it's an accounting system for electrons. So we're trying to keep track of where the electrons have been, where they're coming and going, and if something is gaining or losing electrons. And that's going to help us understand and be able to work with oxidation reduction or redox reactions. So let's go ahead and jump into this, and hopefully this will be helpful to you. Don't forget to like this video and hit subscribe. Okay, so let's cover some of the rules for oxidation numbers. And I think that, one of the hard parts of oxidation numbers is students often tell me, they're like, well, is it like charges? Is it, like chlorine can have a negative charge of 1, or oxygen can have a negative charge of 2. And it's not really like charges, although there is sometimes some overlap, so that can be confusing. But really, like we had talked about earlier, it's just an accounting system. And so just the easiest way to do it is to kind of just follow the rules. And I'm going to cover these rules right now. And these rules should maybe help you be able to take on most anything you're going to hit, at least at this level of chemistry with oxidation numbers. Okay, so let's go ahead and get started. The first rule is that neutral atoms and compounds that consist of one element, they have oxidation numbers of 0. So, for example, if we're looking at your diatomic elements like hydrogen or oxygen, basically those are going to have oxidation numbers of 0. Each hydrogen will be considered an oxidation number of 0. Of course, single atoms like helium would also have an oxidation number of 0. Even things, like S6, since it's all sulfur, it's going to have an oxidation number of 0. Or, even something like a cobalt metal that has lots of atoms that are metallically bonded together, it's going to have an oxidation number of 0. So that's the basic rule that you'll start with. Okay, the second rule is oxidation numbers in a neutral compound will sum to 0. So what does that mean? So if it's a neutral compound like water, like H2O, then when we do the oxidation numbers for oxygen and then hydrogen, and when you add all that up together, and we're going to do some more examples in a minute, but just for this quick rule, this oxygen is -2, and the hydrogen is going to be +1, but there's 2 of them. So when you add all that up, it's going to equal 0. So when you sum up the oxidation numbers for any neutral compound, then they're going to sum up to 0. Now, consequently, when you sum up the oxidation numbers for, like a polyatomic ion, NO3 minus or something like that, then that's going to, instead of summing to 0, it's going to sum to the charge of the ion. So in this case, it would sum to -1. In other words, oxygen's still going to be -2, and there's going to be 3 of them. We'll cover the details of that in a few minutes. But when you add it all up, it's going to be equal to -1. The same thing is going to hold true if you've got something like Cl minus, then there's only one of these, so its oxidation number is going to be -1. If you've got Na plus, then its oxidation number is going to be +1 because it's going to have to sum up to the charge of the ion, and whether it's a polyatomic ion or whether it's just a regular ion. So that is, I think, pretty straightforward. So in addition to that, now that we're talking about these ions, when we're looking at these group 1 metals, they're always going to have an oxidation number of +1. And these group 2 metals, they're always going to have an oxidation number of +2. So that's kind of a hard, fast rule that you'll always keep in place there. And a lot of times these are going to form ionic compounds anyway. And so they'll often be ions. And then, of course, their charge would match their oxidation number. In addition to that, now hydrogen, as you remember, is not really a metal. Now, it's going to be a +1 if it is bound or in a compound with a nonmetal. So if it's in a compound with a nonmetal, it's always going to be +1. But if it is in a compound with a metal, then it's going to be -1. So that can possibly be confusing, but a lot of times you'll see a lot of organic compounds that have hydrogen in them. And if they're covalently bonded with nonmetals, then it's going to be +1. If it's bonded with metals, it's going to be -1. Another rule that you'll typically run into, as a general rule, oxygen is going to be -2. So the oxygen atom is typically going to be, now I'm not talking about O2 because remember O2 is going to be a neutral compound. I'm talking about oxygen, if it's bound up with something, is going to typically be -2. However, if we have what we would refer to as a peroxide link, like here's hydrogen peroxide, you got two oxygens bound together, then in that case, the oxygen is going to be equal to -1. Now, you don't see a lot of that, but you can run across it. So it is important to kind of remember that's kind of an exception when you have this peroxide group with an oxygen bound to another oxygen. But as a general rule, oxygen would be -2 in a compound, not in its diatomic form, in a compound. One other thing that we really have to keep in mind when we're doing these oxidation numbers, you're often going to have a lot of these compounds that are going to have, nitrogen, oxygen, fluorine, carbon, chlorine, bromine, sulfur, phosphorus. You remember, oxidation numbers is not the same as the charge of the element. So as you guys remember, this group typically forms was going to form -1 ions. This group forms -2. This group forms -3. And so you kind of used to that. Now, if we're talking about things that are bonded together, then as a general rule, you're going to follow the more electronegative it is, then that's the one that's going to keep its normal charge. In other words, if something's bonded to fluorine, fluorine will be -1. If you got a nitrogen and oxygen compound, then oxygen is going to be -2. The nitrogen is just going to fall where it falls based on the other elements. Okay, so when you're working through the oxidation numbers of compounds, you always start with the most electronegative first and then work backwards from there. These rules, you can look at them, but really what we have to do is we have to work some examples. That's the only way that you're really going to be able to get a handle on this. Let's hop over and work a few examples, and I think it'll make it more clear. Okay, so I went up and put the rules up here on the left so we can see those rules and work through them as we go. And I've got a few up top and then a few down bottom that we'll look at. So let's start up here at the top at this sulfate ion. And if you remember, the oxidation number of ions will sum to the charge of the ion. So we know we're looking for an overall charge or an overall sum of -2 because this has a -2 charge. So let's start. And we know in this group that oxygen is more electronegative than sulfur. So we're going to set it equal to -2. And so we know we have 4 of those. So we know that that's going to give us a -8. We know we got to wind up with a -2. And so sulfur must be +6. So basically, in this particular case, we're going to say that sulfur, the oxidation number is +6, and oxygen is -2. All right. What about S8, one of the allotropes of sulfur? So remember, this goes back to the first rule up here that atoms and compounds consisting of one element are going to have an oxidation number of 0. So in this particular case, S equals 0. Okay, now we have hypochlorous acid. And if we look at this one, let's start with some of our rules. Remember, hydrogen, when it's bound to nonmetals, is going to be a +1. +1. And oxygen is going to be, it's the more electronegative of these two. So it's going to keep its charge of -2. So the chlorine has got to be +1 to make all this add up to 0. So it's going to be, final answer, H equals +1. Cl equals +1. O equals -2. All right, now we got sodium nitrate. Looking down through our rules, we see that the sodium has got to be, all the group 1 metals have got to be +1. Of course, if you look on the periodic table, oxygen is more electronegative than nitrogen, so it's going to be -2. This is a neutral compound overall, so it's going to sum to 0. So we've got +1, then we got the -2, but there's 3 of these oxygens, so it's going to be -6. And so that means our nitrogen has got to be +5 if it's going to sum to 0. So we've got sodium equals +1. The nitrogen equals +5, and then our oxygen equals -2. Okay, let's look at our aluminum oxide. So let's go ahead and start with the oxygen is -2. And then when of course, there's 3 of them, so we've got -6. We're going to sum to 0 because it's a neutral compound. And then there's 2, this time there's 2 aluminums. So we know we've got to have a total of 6 here, but since there's 2 of them, then the aluminum must be a +3. So +3 times 2 is +6. So then that gives us the aluminum equals +3. And then our oxygen equals -2. Okay, and next we've got our potassium dichromate. So when we go through our rules, then you're going to see that potassium, remember, has got to be a +1, but there's 2 of them. So we've got a +2 here. The oxygen has got to be -2. So, but there's 7 of them. And so that's actually -14. Oops. Let's try that again. -14. We know it's neutral, so it's going to sum to 0. So in this particular case, we have got to get a +12 to make it sum to 0, but there's 2 of these chromiums, and so each one of them is going to be +6. So then when you add all this up, +1 times 2, +6 times 2, -2 times 7, it all sums to 0. So that's going to give us our final. Potassium is +1. Chromium is +6. And oxygen is -2. Now, hopefully that's pretty straightforward to you. Just a little bit of practice, and I think you'll be able to get it if you'll just follow these rules. It'll start making more sense to you the more you practice it, and you won't have to look back at the rules as much. So let's take a look at these. These are various carbon-containing compounds, and let's take a look at how the carbon actually changes or is different, has different oxidation numbers in different compounds. So let's first look at carbon dioxide. And so, oxygen is the more electronegative. So we're going to say it is -2. This is a neutral compound, so it's going to sum to 0. -2 times 2 is -4. So that means our carbon must be 4. So in this case, we're just going to do the carbons so you can see how they change. The carbon oxidation number equals 4 +4. Okay, now let's look at formaldehyde, H2CO. So let's look at our rules. Got to have a +1 for that hydrogen. That means it's +2. We're going to do the carbon last since it's the oxygen's more electronegative. And so we know the oxygen is -2. So in this particular case, you're like, wait a minute. they already sum to 0 because it is a neutral compound. And so in this particular case, your carbon is an oxidation number of 0, which is actually, it does happen, but it's not always super common to see that in a compound. Now let's look at carbon monoxide. In this case, once again, oxygen is going to be -2. Of course, we got to sum to 0, so that one's pretty straightforward. Your carbon is going to be +2. Here, your hydrogen, if you look at your rules, is going to be +1, but you got 4 of them. So you've got +4 total. And remember that the reason that the hydrogen is +1 is simply because it is bound to a non-metal. If it were bound to a metal, it would be -1, but it's bound to a non-metal, so it is a +1. So that means in this case, your carbon is going to be equal to -4. Now let's look down here at this last example. And once again, don't be thrown off by the fact that all your hydrogens are not together. They're going to be +1. And so there's 1, 2, 3, 4 of them. So you've got a +4 here. And then you've got an oxygen, which is a -2. And that all has to sum up to 0. And so in this particular case, once again, your carbon has to be a -2 because -2, and then 4 sums to 0. So your carbon is -2. So it's actually interesting to see all the different ways or all the different oxidation numbers that carbon can have. So you can see this is not really tied to a charge, so to speak, although there is some overlap because the most electronegative element keeps its normal. It keeps the normal charge as its oxidation number. So hopefully that's helpful to you. And in a future video, we'll take a look at an application of this. We'll look at oxidation reduction reactions and how to use oxidation numbers to tell if you've had a redox reaction. And this is going to be essential to that task. So this is really just a building block to get to redox reactions. So, okay, guys, I hope that was helpful to you. And we're going to be following this up with some more oxidation reduction type videos. We're going to learn how to balance those types of equations in some future videos. So stick with us and hit the subscribe button, and I'll hope to see you guys again soon.